Okay, thank you, Michelle, for your introduction, and thank everybody for being here today, listening to me. And as Michelle was mentioning, my aim today is to show you our intended work for the simulation and implementation of a Cape Open new unit operation for the catalytic plate fin heat exchanger for hydrogen liquefaction processes. So the first question is, why do we care for hydrogen liquefaction? So liquefied hydrogen is primarily used in storage and transportation because due to its lower volumes and higher densities, it is better as a energy vector to be transported worldwide, either via land transport or through marine transport, or also as a storage mean, using also its capacity to be transported and being stable at lower temperature inside storage tank. So the hydrogen market for the EU scenario is going to be quite, it's going to increase in the coming years. So in the, as a report of the European Commission, we are expecting to see an increasing demand for hydrogen as a mean of energy, and also for a mean as also for an energy vector in case of fuel, and also as a, let's say, power and energy itself. So in a conservative scenario, we can see that there are from here to 2015 an increase of 4,455 terawatts per hour of hydrogen power requests. So in this scenario, based on the current production of hydrogen, we can see that the power plants, liquid hydrogen plants that are existing right now, they represent a production of a mean of 20 tons per day for the North America scenario until 2009. And they also, it's a different scenario for Europe, where the size of the plants is smaller, with just a 6.1 ton per day of production. This may be due to the difference in the market requests. Maybe in the USA and in North America there is more requests for aerospace applications that in Europe is lacking. So basing on the European scenario, with a 6.1 ton per day plant size of hydrogen liquefaction, we can see that if we take the most conservative scenario of 85 terawatts per hour yearly, that is going to be the transportation hydrogen, as you can see on the right side of the graph. So let's suppose that we take the 100% of this 85 terawatts per hour of hydrogen, and we want to liquefy them at all. So by some calculations, we can see that the LHV of hydrogen is 120 megajoule per kilogram, which is a standard value. And if we calculate the mass that is required of hydrogen in order to obtain this 85 terawatts per hour, is going to be 2.55 megaton of hydrogen, which in turns gives a daily production with an annual operativity of a plant of 90% of the time of 7,763 tons per day, which in turns gives us a value of the approximation of new plants that are going to be constructed in this time frame. So from now until 2015, we probably we can expect to see some new plants constructed, and by using the size of the medium plant that is existing right now in Europe, we can see that with 6.1 ton per day of production, we can expect to see approximately 1,200 new plants, which in terms, we can say that at least we have to simulate at least one plant and copy-paste it in 1,200 new simulations every time. So by this number, we can see that there is a demand for the simulation of these plants. And the core unit that I want to speak about is the catalytic heat exchanger for the hydrogen liquefaction. So why it is an important unit? Because in hydrogen liquefaction, we have a different kind of hydrogen. So there is not just hydrogen, but there is ortho-hydrogen and para-hydrogen. Ortho-hydrogen is the hydrogen with spin of the protons that are going in the same direction, while para-hydrogen is going in different directions. And these two species of hydrogen are not just some simple isomers, but they are very important in the thermodynamic process, because these two have a conversion that is going on between one and the other, and they are kinetically very fast, and also maybe let's say they are instantaneous as a kinetic reaction, and they try to reach the equilibrium very fast in this way. So we have para-hydrogen, which is the most stable species at low temperatures. Approximately, we have the 100% of liquid of para-hydrogen at 0 Kelvin, and ortho-hydrogen is more higher in percentage if we go to higher temperature. We reach the normal hydrogen composition, which is the 75 and 25% of ortho-hydrogen and para-hydrogen, which is the hydrogen that we can expect to see at room temperature, at standard temperatures in our, let's say, daily lives, if we use hydrogen in our daily lives, but that's another question. So the equilibrium hydrogen is a pseudo-species, which is a kind of non-existing species that is just the curve that is selecting the composition of ortho to para-hydrogen at different temperatures, as you can see by the graph on the right side. So the simplest liquefaction process is the traditional Claude process, where we can see the compressor that is the first stage of this process. After the hydrogen is fed to the compressor and is going inside a cooling area, the hydrogen is then expanded in order to lower its temperature, separated between saturated liquid and saturated vapor. The liquid hydrogen is stored, and the vapor is fed back to the chilling area in order to lower the temperature of the coming new feed of hydrogen. There are many new different implementations and innovative implementations of this process, but this is just the simplest one, and is also the let's say most robust in terms of implementation. But nevertheless, the main important point that I want to stress on is the fact that in all these processes, even though it's the traditional Claude process or the most innovative ones, the core unit is the catalytic plate fin heat exchanger, which is a kind of heat exchanger, which is a plate fin heat exchanger, the one that you can see also in air separation units, but it is very different because it is also filled with a catalyst, which is a hydrospheric oxide catalyst, which due to its magnetic properties, it is able to shift the ortho-hydrogen coming from the normal hydrogen composition of 75 ortho-hydrogen and 25 para-hydrogen composition to all para-hydrogen, because due to its magnetic composition, it spins the protons of the hydrogen in different ways. So these hydrogens are not just these heat exchangers are not just some simple heat exchangers, because they also are a sort of reactor indeed. So in simulating these systems, we use the most suitable tools that we have in our daily life, in our daily simulation life. Yeah. And this is an example using the Aspen-ISIS platform, where we can see that the heat exchangers are simulated in different parts. These are multi-stream heat exchangers with nitrogen cooling in this very case. And the main point that I want to stress on is the fact that these processes can be simulated using the tools that we are used to use, actually. So in reality, these heat exchangers that we can see simulated using 7, 8, or maybe more heat exchangers are just one big unit. That is the brazed aluminum heat exchanger that you can see in this figure. This is not the kind of heat exchanger with the catalyst inside, but it is indeed the same type of reactor without the catalyst inside. So about the simulation of these heat exchangers, we do have some, let's say, methods to simulate them right now, but these are not very, let's say, rigorous methods. The current solutions to simulate this unit of operation is, first of all, to add new duties in this heat exchanger after each heat exchanger. So the hydrogen is fed to the first heat exchanger, it is lowered in temperature, and a new duty stream of hot stream is inserted at the end of the heat exchanger. This results in a energetic balance being respected, because the heat of the reaction that is created going from the ortho-hydrogen to para-hydrogen, because the problem in this case is that the ortho and para-hydrogen, when they get converted from one species to the other, they generate heat, just like in a normal reaction. So when generating this heat, this lowers the efficiency of the heat exchange, because there is now not only the difficulties of the low temperature approach of these heat exchangers, but also the lost duties due to the reaction of ortho-hydrogen to para-hydrogen. This is the first method, where we can take one heat exchanger, add one more duty, heat duty, to the end of this heat exchanger, and try to calculate the amount of energy requirement. This is not rigorous, and it gives inaccurate results, because the convergence inside the heat exchanger does not include the presence of the duty at the end of the heat exchanger. So it is not a rigorous method. It can give approximate results that are going to be useful in the first instance, but they should be implemented in a different way. A different method, which is maybe more rigorous but very difficult to implement, is to use a new kind of pseudo component, which is the equilibrium hydrogen, and we need to enter the train of heat exchangers by splitting the hydrogen feed, which is normal hydrogen, cut this stream of normal hydrogen, and transform this stream in a new component that is equilibrium hydrogen. In aspenasis, you can do that using the cut unit, and then after you go at the end of the heat exchanger, you make another cut and go back to only para-hydrogen, or maybe the percentage of para-hydrogen that you had calculated. In this case, the pseudo component, that is equilibrium hydrogen, must take inside its heat capacity also the heat of reaction. So it is a fictitious heat capacity, which also represents the heat of reaction of the hydrogen reaction at any temperature. Another different method is a linkage to an external tool like Excel, for instance, using maybe some developed models, but this is actually not a solution, because it is cumbersome, it is slow, and it is also difficult to implement. So our intended solution is to use the Cape Open unit operation based on the COBIA interface, where we can simulate a rigorous model of a catalytic plate fin heat exchanger with a finite difference method, where the unknown temperature, may then be the inlet temperatures or the outlet temperatures, are calculated after a convergence cycle inside of an heat exchanger. It is not a maybe a new kind of let's say completely new system or maybe a completely new implementation. It is just a simple heat exchanger, maybe modeled in a rigorous way where you have also multiple streams of cold stream and hot stream, but they also have some part of the heat exchanger with reaction going inside, and it is also creating the external duty coming from the heat of reaction in this case. Then the usage of the COBIA interface is very much appreciated because it is easier to use it due to the class wizard. The customizability is way more easier and faster. So new implementations and new features may be added very fast. And it is also very much appreciated for the forward and backward compatibility and also for the platform independence in this case. So in conclusion, by using this method, we want to solve the problem of the ortho-to-para hydrogen conversion and the simulation of the ortho-to-para hydrogen conversion. And by using the unconventional, by using the Cape open structure to simulate an unconventional unit of operation, which is the, let's say, one of the main interests in using the Cape open protocol, actually. And by using COBIA, we can do that more efficiently. In the future, we will like to integrate a UI for the user in order to be able to implement maybe new features and new additional properties by using also the iCape utilities and maybe in creating this kind of catalytic heat exchanger for new and different processes outside of the ortho-to-para hydrogen conversion. And also maybe when the chemical reactions interface written in COBIA should be released, we would like to start implementing the ortho-to-para hydrogen reaction kinetic for a simulation-wide system. And thank you for your attention. And if you have any questions, please ask me.